So thank you for having me today. Yeah, so I'll be presenting on, I'll be presenting on mainly focusing on fatigue loads and how these the uncertainty kind of it changes based on the turbulence box that you choose when you use an aeroelastic simulation, and I'll be focusing on three aspects. So the quantity of turbulence boxes, which is how many simulations you run, the resolution of the turbulence box, and also something called scaling of the turbulence, which I'll explain a bit later. And yeah, so this is work I did back at DTU for my PhD, and now I'm sitting at MIT as a postdoc. So, so a bit of background of how this fits into wind farm control. So with all these new control strategies coming out, it's important to to test if these strategies are actually would actually work in a real wind farm. And one way you can do that is to use aeroelastic simulations. And there's two things that this does. It allows you to see how your controller behaves in a dynamic setting. So with realistic turbulence, and if it can perform in a closed loop manner. And the other thing is you can also quantify the fatigue loads as you have hopefully load time series, and from that you can see if you're increasing or decreasing the damage in your turbines. And on the right here we have an animation from a previous study I did where I did yaw steering, and there is a power increase. But what I also wanted to see is how the fatigue loads were influenced, and I wanted to set up this simulation in a way which actually could, in an unbiased and somewhat accurate way, say what the fatigue loads are and how they increase or decrease. And in the manuscript, which isn't available yet, but it should be available any day now, I have a sentence saying, to ensure unbiased fatigue load calculations, the resolution of the turbulence box is set to approximately 60 grid points per rotor diameter in all spatial directions. So this presentation would kind of just dig into where this 60 grid points per rotor diameter came from. So as I mentioned, this is from a previous study. This the paper you can refer to for everything I'm going to present is from the last talk conference, and it's work that I did with my supervisor Gunnar Larsen. And yeah, so I'll be quantifying uncertainty and turbine fatigue loads, and then I'll also be giving a few recommendations based on the study that I did. So so as Eric mentioned, I guess the fatigue loads don't come up too often, so I'll just give a quick overview of how we quantify them. So we use a quantity called the damage equivalent load, which is a way of describing damage accumulation in a component. So how this works is you get your time series of your stress from your aeroelastic simulation. This could be like a blade root or the tower or the generator shaft or something like that. And you have some complicated time stress series. And the idea is that we want to find a way to sum this up into a single number to say how much damage is being caused. And the first step is we do something called rain flow counting, which is where we count the number of cycles and the amplitude of each of these cycles. And the size of these half cycles has a different amount of stress accumulation. Then we use the Miners rule and to determine this quantity called the damage equivalent load. And so we get all the stress cycles, which are S. We have a Wohler exponent, which is M, which says how much these large oscillations accumulate damage, and a higher number means that larger oscillations are worse in terms of creating damage. And we were asking if we have a simple sinusoidal, a simple kind of periodic signal, what amplitude does that need to be to have the exact same damage accumulation as this complicated signal? And the amplitude is the damage equivalent load, or the peak-to-peak amplitude. So with this, we can take any time series of loads, and we can easily compare them and say this one creates more damage or this one creates less damage. So it's useful for comparing if a control strategy increases or decreases your fatigue in certain components. So yeah, and I'll just go back. So there's a few things which influence fatigue load calculations. Firstly, you notice it's a really complicated kind of statistic to work with. It's different to working with mean or standard deviation because it's a bit more difficult to calculate. It's very sensitive to stochastic realization. So if you have a different seed, you have a very different damage quantity. The resolution, which I'll show later, is quite important, like how resolved your wind field is. High frequency turbulence, I'll also describe that in a moment. And something else is the wind field heterogeneity, which is like if you have more wind on the left or the right of the rotor. So like it really depends on what's happening spatially in over the rotor. So it's quite sensitive to a lot of things. So I'll just go over a few of them, and these are the ones which I'll describe in the study. So the first is the number of stochastic realizations, like how many seeds. We often run 6 seeds for fatigue simulations, 6+, and that's recommended by the IEC standards. They recommend that for 10-minute simulations, and this is usually a single turbine simulation. And yeah, the question always comes up, is this enough? And if you look at what it says in the IEC standards, it says we need, our simulation should be statistically reliable. What does that mean? So I'm digging a bit deeper into how we can, like, why it's 6 seeds, or maybe if it needs to be more than that. It typically does need to be a bit more. The other aspect is the resolution of the turbulence box. So we use these normally pre-generated turbulence boxes to in aeroelastic simulations to to simulate a turbulent wind field. And there isn't much recommendations regarding the what resolution there should be in the IEC standards. There is a pretty much one sentence saying that attention should be given, and then in a footnote it describes in words this equation, which kind of gives a guideline of what minimum resolution you should have for your turbulence box if it was in a like a Cartesian grid. So if we take this recommendation and we get a reference turbine and we want to run a 10-minute simulation, I think at 10 meters per second, you would get you can get away with a resolution of this. This is just a number. And the question is this enough? Like, does this recommendation make sense? And like, how do you even quantify it being resolved? So I'll dig a bit more into that. And the last thing is this turbulence scaling, which is something that we sometimes do when in aeroelastic simulations, at least, where we have a turbulence box and we want it to be a particular turbulence intensity, but it's not the turbulence intensity we want it to be. And what you can do is you can just kind of scale every point in the turbulence box. So on this left figure here, we have the spectrum of a number of turbulence boxes. Each line is a different turbulence box, and this is the spectrum. And we can see they are different turbulence intensities by the color of the line. So the color represents what the turbulence intensity is of each of these boxes. And we can see that it's not the same turbulence intensity. So if you perform some kind of scaling, you can get to this right plot here where all the lines are now the same color. They have the same turbulence intensity. This was done by shifting the spectrum up and down, which is essentially what happens when you scale every point. But the issue here is that now the spectrum, especially in the high frequency area, has a wider spread compared to what it was before on the left figure. So yeah, this region here has more variations compared to this one, and this is an issue because it's actually the frequency range which is important for turbines, like the dynamics of the turbine respond to this area. So by actually getting the correct turbulence intensity, you are creating more distortions in the frequency range, which is important for fatigue loads. So my argument here is that you shouldn't be doing this. It's better to have variations in your turbulence intensity and to have a more accurate spectrum. Otherwise, you will get distortions, and as I'll show in a moment, it will cause a larger spread in fatigue load results. Yes. So these are the three things I wanted to test, and to do that, I set up a set of simulations. They were 10-minute simulations of the D2 10 megawatt. I was using Hawk 2 for the Aeroelastic simulator. So it's just a single turbine. And I wanted to vary the resolution in all spatial directions, so the longitudinal resolution, as well as the lateral and vertical resolution. And to keep it simple, I kept the vertical and lateral resolution equal to each other for each simulation. So it's like 2 by 2 or 256 by 256. I also ran for each of these resolutions. I used the two different scaling methods, the target spectrum and the target variance method. And for every single combination, I ran the simulation 200 times, so 200 stochastic seeds for every single combination of these. So in the end, I had just under 20,000 simulations. And yeah, from this, I wanted to, get to the bottom of it. Like 200 seeds is more seeds than you could conceivably ever run for any kind of validation. So hopefully it was enough to get to some kind of useful conclusion. And when I ran those simulations, after that, I computed some of the fatigue loads, the damage equivalent loads of 6 of the components. So blade, flapwise and edgewise. Yeah, so tower and also the main shaft. And I kept some of the other parameters fixed, like the wind speed. I kept it at 10 meters per second, and I chose that because it was close to the rated wind speed, which is typically when the loads are quite high. So it's more conservative, I hope, at this wind speed. And I just kept the turbulence intensity at around 10%. Yes, so all right, so let's dig into the results, and I'll walk through this because there's a lot of data on the screen here. So what this is, this is the results for what happens when you vary the lateral and vertical discretization. So we can have, I started low, like 2 points, like a 2 by 2 grid over the rotor, and I go all the way up to 128. Actually, I go up to 256, but I'll explain why that's not here in a moment. So this is, so all the way up to 128 by 128 points over the rotor. And there are 2 distributions. The one on the left, the blue one, is the target variance method. This is where I described that you do perform some kind of scaling to get the turbulence intensity you want. And this is the one I recommend against. And then the other one is just to keep the spectrum as it is and to have the average turbulence intensity equal to what you want. So it's not necessarily equal, but on average it is. So yeah, so the orange one is what I recommend, and the blue one is the one I'm recommending against. And yeah, so there's a few takeaways we can take from this, and I'll just direct you to some of them. The first is the target variance method, that is performing a scaling on the turbulence box, consistently overestimates the fatigue loads. I performed this scaling as described in the Hawk 2 manual, so it is commonly used if you're using the default kind of Hawk 2 results kind of methodology, and it's consistently higher. This blue line is just it's overestimating the fatigue loads for all of these 6 components. The other thing is ignoring the upward bias of these blue lines. We also notice that the spread of the blue distributions is much wider than the orange ones, which is without scaling. And I just highlighted a few of them where you just see the spread is just much larger than on the left than on the right. So this makes it more difficult to get an accurate mean damage equivalent load, because you have such a large spread. You're going to get more uncertainty in your answers in the end. So so essentially, I pretty much ruled out that the scaling method, and I've said, we should just go with this target spectrum method on the right, these orange distributions. And the other thing which was very nice to see was that the damage equivalent loads seemed to converge as you increase the resolution. This wasn't, this wasn't obvious because, it just kind of wasn't clear if this would actually happen, but it did happen, which was nice. And so it's everything makes sense in that. I was happy with that. So the IEC standards recommended from what I showed before, you can get away with 32 points over the rotor. Is this converged? I'll get to that in a moment. Now, this is another figure. Now, instead of the lateral and vertical discretization, I'm looking at the longitudinal discretization. So this is along the free stream. How many grid points do you have over this 10-minute turbulence box? And it's, yeah, similar plot. We have some similar conclusions. The target variance method consistently overestimates the fatigue loads compared to not scaling the turbulence box. So blue line is higher than the orange line. The blue distributions are wider. So yeah, so I've safely concluded that, you know, for the rest of the investigation, I don't use this scaling approach. So I'm only focusing on the orange approach, which is, you know, keeping the spectrum consistent. And yeah, we see, yeah, so IEC standards, you can get away with 1,024 points longitudinally over this 10-minute turbulence box. The Hawk 2 default is quite high. It's just over 8,000 points. Yeah, in the end, what I recommend is actually somewhere in between, but I'll get to that. Excuse me. Okay, so yeah, we have these distributions and we can kind of see that they're converging, but I wanted a more rigorous way to quantify it. So I use the Welch t-test, which is it's a t-test. It determines if the mean of two distributions is potentially equal, and if it's a way of comparing two distributions. So as I don't have an actual like solid reference case where I know what the fatigue damage is, what I used was the highest resolution simulation that I had from this simulation set, and I said, okay, this is my converged result. It may not be 100% converged, but it's my reference case. And then I compared every other distribution with that. And if it passed the t-test, then I would say it's possibly converged. And the way that these t-tests work is you can reject the null hypothesis. So you can say it's definitely not converged, but you can't really say it is converged. So yeah, so you just take that with a grain of salt. Yeah, so here are, okay, here's a complicated figure. I'll walk you through it again. So on the x-axis is the lateral and vertical discretization. So how many points over the rotor. And then in the y-axis is longitudinal discretization along the free stream. And the colors and the numbers represent the p-value or the value of the t-test, like if it's converged or not. So 0 means definitely not converged, or at least the distribution does not match the reference distribution. And green means it's, well, at least greater than 5%, so maybe it does match. As I mentioned, I used the highest resolution simulation results as my reference, and that's highlighted in this red circle here. It's 128 points laterally and vertically, and 8,192 points longitudinally. You will notice that there is a data point missing for the highest resolution, which should have been 256 points here. And yeah, unfortunately, I couldn't, it didn't work. I had computational or memory issues with this. So it's kind of absent from my data. But Hawk 2 has been apparently updated recently to be able to handle these very large turbulence boxes. And so, but unfortunately at the time I wasn't able to get this data point, which is a shame. Anyway, so the recommendation from all of this is that we can see for all of the components here, they are mostly green in this region here. And this comes to my final recommendation, which is for a 10-minute simulation to have a vertical and lateral resolution of 64 points over the rotor or more. And for the longitudinal discretization, it's 2,048 points. So this is higher than the IEC recommendation, but it's it's quite high in the over the rotor. 64 points is quite a lot, especially for LES. It's not that easy to get that many points. But longitudinally, it's actually less than what we normally do in Hawk 2, so we can actually reduce that. And there's something else you will notice if you look closely. You will see that within this square where I've recommended the particular resolution, there's the blade root edgewise and the main shaft. Oops. Oh no, sorry. They're actually not that converged. They're very close to the 5% mark or less than 5%. But in the next slide, we'll show that it's not that sensitive to turbulence resolution in the end. So it's actually, I don't think it's that much of an issue that these particular channels are not converged in the statistical sense, because the difference is so small compared to the actual value. Yes, and then the other question was how many seeds. So we can look at the standard error of the mean for this, and so we can estimate the true, or we can estimate the standard deviation of the of these damage equivalent loads based on all of our 200 simulations of our highest resolution simulations, and we can from that estimate the standard error of the mean, and we can see that you never actually converge. You can only get closer to a converged value, and so from here we can kind of define what it means to be statistically reliable, and that depends on what you prefer. But if you want a standard error of less than 5%, you need to have a particular number of seeds, and it depends on which channel. The most difficult channel is its main shaft torsion, and so if you want to have all of your channels, if these are all of your channels converged within 5%, you need 21 seeds, 21 random generations of your simulation. So that gives you an idea. But if you don't need to worry about the shaft torsion, then you can actually get away with 6 seeds and still be about 5% within 5% of standard error. If 5% is not enough for you and you want to go down to, like, for example, 1%, you need significantly more, like maybe around 500 seeds to get that extra level of accuracy. So this gives an idea just how difficult it is, and like if you want to increase your kind of certainty, you have to deal with this like inverse square root of number of samples. So you just need to have way more simulations to reduce your error. So that's pretty much it in a nutshell, the study that I did. And so the recommendations in the end are pretty clear, but again, where they are valid is another question. But firstly, do not do this turbulence box scaling, as it distorts the spectrum, causing a bias in the your fatigue load estimate. The other thing is 64 points over the grid point, 64 points per rotor diameter in all spatial directions is recommended. And so it turns out the longitudinal discretization is more or less the same cell length as the vertical and horizontal recommendation that I gave. So it's actually 64 points per rotor diameter, or it's about every cell should be about 1.5% of the rotor diameter in each spatial direction. 21 seeds if you want less than 5% error for all fatigue load channels. If you want to go higher than that, you need way more seeds. And there are, of course, some knowledge gaps here. So I used PORC2. It would be interesting to run this on another aeroelastic simulator like FAST or something else, just to see if there are maybe simulation-specific things which cause these particular results. I used only the GTU 10 megawatt. It's not clear if this generalizes for larger or smaller rotors, like this recommendation of 1.5% of the rotor diameter. It's useful to to wrap your head around it, but it's not. I don't know if it actually generalizes to other rotors, like larger or smaller rotors. I only used 10 meters per second wind speeds. There's of course, it may change with different wind conditions. And this is only a single turbine simulation. It is it gives an idea of what kind of resolution you need for a farm level simulation, but there's still kind of a knowledge gap there. Like once you include wakes as well, like non-homogeneous wind field, does this change? Like, do we need higher resolutions, or are there other sources of uncertainty? But but that's pretty much it from me. If you want to refer to the work here, it's available. It's from the last talk conference. So yeah, feel free to have a read of that. And yeah, I'm open to any questions. So thank you.
Yeah, very nice talk. Thank you, Jamie. Yeah, so feel free to raise your hand or just ask a question or type in the chat as well. Looks like Nathan, you're first.
Sure. Yeah, very nice presentation. Neat piece of work. Thanks. I'm curious, as we think about using this for wind farm flow control comparisons, you were looking at sort of that absolute value or variability in the absolute result of damage equivalent load. We wanted to compare, say, with and without a wind farm flow control strategy. Could you run the same seeds for both and get a comparative value with lower uncertainty, even if the absolute value is high? Does that make sense?
Yeah, I mean, that's a good way to do it, to test like case by case, like what would happen in a very specific scenario with and without control. So it is good. But once, I think it's yeah, I guess what this is more focusing on is the statistical sense. So like when you want to kind of get, instead of like focusing on a single case, you want to get an idea of how it would work on average over all cases. And yeah, so I think
absolutely, no, that makes sense.
Yeah, and also when you're comparing like control strategies, and I'm not sure if everyone agrees, but like I don't think it really matters what the absolute value of the fatigue load is. It's more about getting an idea if it's increasing or decreasing, especially in the simulations. Like when it comes to more like estimating the exact value in a wind farm, and having you need very accurate like kind of models and things. But when it's just comparing, I think it's more, I guess, informative just to know if it's increasing or decreasing.
Yeah.
So yeah,
I would argue it can matter if we're trying to like say, make an argument that there's sufficient margin in the design relative to a specific wind farm to increase the loads by a certain amount and still be safe. But anyway, very nice. Thanks.
Thanks.
Fernando, I think you're next.
Yeah, can you hear me?
Yes.
Yes.
Hey, James, very nice presentation and very nice work. First of all, I was curious about whether there is an extension of this work for extreme loads in addition to fatigue loads. And if you have any insights into what to expect there in terms of difficulties or let's say new things to take care of.
Yeah, that's a good question. We, like Gunnar and I were talking about this, and we decided just to focus on fatigue loads for this one, as extreme loads are just, they're calculated very differently to fatigue loads, and it's just yeah, I think there are many other considerations when it comes to that, which I guess I'm not too familiar with it because I'm mostly focused on fatigue loads. But it's just, yeah, I think it would be very interesting to do and like a follow-up focusing on extreme loads, as it's a bit more, I guess, yeah, I think it can be a bit more difficult to get answers in a similar way that I did in this study for extreme loads. But yeah, I'm not too sure about the how that would be done, as we didn't really go on with that. We just focused on fatigue loads for the study, and yeah, left it at that.
Okay, thank you.
Paul, do you have a question?
Yes, thanks again for the presentation. So first part was, does this hold also for wake? So when you are in, I mean, this is a quite nice wind field. Yes, there's turbulence, but when you go into wake, you have some discontinuities almost, or at least some steps in wind shear, very different wind shear. And maybe the resolution then needs to be. Now I'm not a flow expert, I'm a control engineer, but I'm thinking what resolution could be very different, what you need there to represent the loads well when you have this waked shape. Any comments to that?
That's a good point, and that's, yeah, as I mentioned, it's not like I can't really answer that from the investigation I did here, but yeah, it's a good question. Like, what if does this actually translate to wind farm level simulations? And I suspect it does, as the resolution is quite high, like 64 by 64 over the rotor, which is, I think it's enough to represent the wake shape. And in another study, which is also going to be coming out soon, I presented it at Deep Wind. It was looking at some of the dominant mode shapes that influence fatigue loads, and they're normally quite large kind of shapes, which it's a bit hard to describe here, but like you have like partial wakes or a full wake, or like double wakes, like on left and right, and wind shear. So they're kind of these quantities which happen over the rotor. I think they're quite kind of low resolution effects. So I think there are ways you can represent the loads with a lower resolution than what I've recommended here. So yeah, it's a bit hard to describe here, but I think I suspect it's enough, like the resolution that was recommended here. And if it was actually any higher, it would just make everyone's life difficult, especially if you're running LES, because the resolution which is recommended here is already very high, I think. So
thanks.
All right, Torben, I think you were next.
Yeah, I was wondering if you can see any effect of the Wöhler coefficient, because you could think that the high Wöhler coefficients loads would be much more sensitive to more seldom and extreme excursions in wind. So you expect that it would be easier to estimate, steel loads than glass fiber loads. Or...
Yeah, that's a good point. I only looked at the kind of typical values that you see. So it was 10 for the blade components and 4 for the steel components. So that would be interesting to see. I would also assume it's more sensitive for the high Wöhler exponent. But I did find, we can look back here, for the main shaft, which is steel, so it's like a steel component. It had for some reason it had these very large long tails. So there were some simulations which just had very high damage equivalent loads, and these were I would say relatively low Wöhler exponent compared to the other ones. I mean, it's 4 compared to 10. So
it's more or less the opposite of what I'm suggesting, because I also noticed you said that the main shaft was a problem, and that's after all steel. That was surprising to me. I would think that blades would be more difficult.
Yeah, it seems like, I guess it seems like over the 10-minute simulations, there's at least a converge result, but it seems there's more variability in the simulations with the main shaft. But yeah, the main shaft is a bit of a mystery to me. It's quite interesting. But yeah, I think with at least the blade elements, it seems like they converge more or less to a result. It will be interesting at least to see what the effect of Wöhler exponent is. But yeah, I can't really conclude on anything based on the simulations that I've done.
Okay, thanks.
All right, thanks. Julian.
Thanks for the very nice presentation. Actually, on this slide, this was where my question was. Like, I don't see, like, I didn't really follow the logic. If I was wondering if you could reiterate it, like, why is one of these better than the other? Like, I get that there's more spread, but maybe that's a good thing. Like, if you don't want spread, just use one turbulence seed. I mean, I just don't see, maybe you could just reiterate why you recommend one of these over the other.
Yeah, so in terms of the spread, the idea is that if you just run one simulation, you're going to have one point in this distribution, and the idea is you want an estimate of the true value or the mean value, and so you need to run many simulations or get many data points over these distributions. And if your distribution is spread quite wide, then the error of your mean will be greater if you have a bigger spread. And whereas if you have a better represented spectrum in the region which affects fatigue loads, it seems like the fatigue load quantity becomes more consistent, and as a result, you get these narrower distributions, and you can actually get away with less seeds if you were using the orange distributions rather than the blue distributions. So that's the main idea. Like, it's more about when you run when you want to estimate the mean from a sample.
Well, thanks for clarifying. I really appreciate it.
Yeah, no worries.
Yeah, good question. Soren, do you have a last question?
Yes, thanks, Jamie, for the very nice presentation, and nice to see you. I had you comment a little bit on this with that it's of course uncertain how generic this is for different turbines. But could you maybe comment on how many nodes your Hawk 2 model has, like radially? Because I guess that would relate to this 1.5% of the radius recommendation that you have. Because
that's a good question. And I don't know off the top of my head. I would have to look into the model, but I just used the default DT10 megawatt model. But I had a feeling this question would come up. So yeah, so thanks, Soren. But that's another good question. Like, because I'm increasing the resolution so high in the turbulence box, it would have made sense to also look at like changing the number of points in the nodes on the blade. But yeah, I'm not sure. That is a good question.
Yeah, fair enough. No, I just wondered because of course they will have an effect, right? If you only have 5 nodes or 5 elements essentially on your blade, then
yeah. So yeah, this is why I think it would be interesting to see different turbine models, or at least different aeroelastic simulators, to see what the differences, and to get an idea what is specifically because of the fact that I was using Hawk 2 for this. Like, it would be interesting to see.
Yeah. Okay. But thanks. Nice.
Thanks.
Yeah, maybe if I could just ask a quick question. Have you gotten any feedback from industry or people who have run a lot of load simulations in the past about like what uncertainty they think is acceptable and what they think about your results?
So I've had the talk about number of seeds with many people, and it's always like, the impression I get is that it's like, we know that it should be more than 6 seeds, but we just stick with something consistent. I did hear I got some interest from some people at the talk conference, and from, I think it was the Siemens office in Hamburg, and they were saying that the main shaft torsion, which is my most challenging load here, they said that they also it's also a load which is difficult to simulate and may not be the most useful fatigue load to be looking at here. So in that sense, this is why I said that if you don't need the main shaft torsion, then you actually do end up with like for all the other things, 6 Cs or 7 Cs is actually enough to be within 5%. So that was interesting to hear. But yeah, then I'm not. That was just from one guy I talked to, so I'm not sure about what others think about that. But yeah, it seems to be like a topic that a lot of people are interested who do run aeroelastic simulations, because it's a study which I think a lot of people do, but it's quite difficult to do because it's like you just need more higher resolution and more seas than is expected. So it's a difficult study.
Right. Yeah. That's really interesting. That the main shaft is just always difficult to simulate the loads for. All right. Yeah. Well, thanks again, Jamie. Really appreciate the nice presentation.